Dr. Prometeo Cortés completed his master's and doctoral studies at the Center for Computing Research (IPN) and is currently a professor researcher at the Instituto Tecnológico de Tijuana, incorporated through the Researchers for Mexico Citedi program since 2017. Dr. Cortés' lines of research are the development of intelligent computing methods and techniques based on machine learning, fuzzy logic, neural networks, evolutionary computing, and meta-heuristics applied to the control and manipulation of robots under conditions of uncertainty. I hand over the word to Prometeo Cortés.
I talk about the need of quantum computing for fuzzy systems in high-dimensionality problems. This work is collaborated with Febrer Valdez, Patricia Melin, and Oscar Castillo. The outline is the foundation of fuzzy logic, quantum computing. I talk about quantum fuzzy inference systems, and finally I dictate conclusion and future works. Fuzzy logic extends classical logic by introducing a continuum of true values between absolute false and absolute true. This allows for more flexible and realistic reasoning in systems where binary logic called false. Fuzzy sets are the foundation of fuzzy logic. They allow us to represent uncertainty by assigning degrees of membership to elements. A fuzzy set can be defined as this equation. Fuzzy set enable the assignment of linguistic values to variables, allowing us to describe imprecise concepts such as low, medium, or high, and those support more intuitive and human-like reasoning. Using linguistic terms derived from fuzzy sets, we can build fuzzy rule-based systems. These systems represent knowledge of if-then rules, allowing for flexible decision-making and reasoning under uncertainty, similar to how humans process imprecise information. A typical rule with a fuzzy knowledge-based framework can be expressed as follows. If we have a system with n inputs, we can relate these inputs with fuzzy values. And computing these fuzzy values, we can imply a fuzzy value to the output variable. One commonly used methodology for building a knowledge fuzzy rule-based system is grid import partitioning. This approach combines each fuzzy sets of a variable with the other fuzzy sets of the other variables, forming a multidimensional grid that defines the structure of the rule base. The total combination of the rules is given by this equation, in which if we have a system with n inputs, and each input are defined with n values, then the number of rules is equal to the n values to n inputs. This equation also is knowing that the course of dimensionality of the systems. Here we can see that for a system of 5 inputs, and each input is defined with 4 membership values, we need to process more than 1,000 of rules. And this is can be represent two different problems or two problems in different directions. For one side, is a challenge to represent the knowledge of this large number of rules. For other hand, we have the problem that the process is expensive in classical computers. Then we call things in process these rules in several devices or different devices, such as FPGAs, GPUs, or the quantum parallels of quantum computers. Okay, this is other numbers of rules related with the number of inputs and number of membership values. Here is figure 1 show fuzzy inference systems. Here we can see that a fuzzy inference system is composed by 4 modules, in which if we have a input crypts value, we can fussify this value and convert this in a fuzzy set. And with a rule-based system, we can process this information and generate a fuzzy set in the output variable. Then if we need a crypts value in the output, we need to defussify this fuzzy set. Well, what about quantum computing? Quantum computers are units or systems that work with qubits. And a qubit is the basic unit of quantum information. Unlike a classical bit, which is either 0 or 1, a qubit can exist in a superposition of both states simultaneously. We say that a qubit is in two states, 0 or 1, and the amplitude of the state 0 is alpha, and the amplitude of the state 1 is beta. At the same time, alpha squared said us the probability to measure the qubit in 0 state, and beta squared said us the probability to measure the qubit in 1 state. Because when we read the qubit state, we can not read the alpha and beta. Only we can read 0 or 1. Here in figure 2, we see a quantum circuit of equal superposition states. We had a Hadamard gate in which a 0 state converts in a state of equal superposition state. Okay, with 3 qubits, we have 8 different states in this circuit. Quantum parallels allows a quantum system to process multiple inputs simultaneously by leveraging superposition, enabling the evaluation of many possibilities or many states in a single computational step. There are constraints in quantum computing. Quantum gates must be reversible, meaning that they are represented by unitary matrix U, and U dagger times U is equal to identity, where U dagger is a conjugate transpose of U. Ideally, we aim to process the entry sets of fuzzy sets using quantum parallels. However, due to current limitation in development and design of reversible quantum gates, this work focuses exclusively on the quantum processing of ruled antecedents. Then the quantum fuzzy inference, we add a quantum inference module in which the fuzzification module sends the activation sets to the quantum inference module, and the quantum inference module sends a string with the formation of the reading qubits. Here is an example of a system with 2 inputs, and each of the inputs has 4 membership values. Okay, the idea is to configure the qubits with the membership values of the fuzzy variable and put at amplitude of the state of the qubits. If we have a variable with 4 states, we need two qubits. If we have 8 variables in 8 values in a variable, then we need 3 qubits. Then if we grouping the qubits by variable, then we have in this part, after the processing this gate, a superposition state with the amplitudes related with the membership values of the fuzzy set. And we can see that the state probabilities derived from tensor product operation are equal to the foreign state via product norms. And then when the qubits are reading, we can send this information, the information that go to the inference module is the rule activated? Okay. With this, we can see that for a system with n inputs, and if we model each input with 2 values, we need the same number of inputs, we need the number of qubits. For a system with in which each input variable is implemented with 3 or 4 membership functions, the number of qubits is equal to 2 times the number of inputs. And here, this is the example that we described before. With a computer with 10 qubits, we can process in parallel step 1,000 of rules. Here is another case in which we have a system with 5 inputs, and each input of is modeled with 9 to 16 values, and we need 20 qubits. And we have a computer that can process more than 1 million of rules in a step. Here we can see 2 cases in which we have a system with high dimensional inputs. We can see that for a system in which the inputs are modeled with 2, 3, or 4 values, we need a computer with 1,000 of 12,000 qubits, and this is equal to 2 times the number of inputs. And the number of rules that can be processed in one step is 1 times 10 to 301. And we can see that for case where the inputs are modeled with 5 to 8 membership values, and with 500 of inputs, we need a computer with 1,500 qubits, and the number of rules that can be processed in one step is not. It cannot represent with a doubling point or with a number in floating point. The conclusions. These articles examine the challenge faced by fuzzy rules-based system when applied to high-dimensionality problems, as shown in Table 1. Even systems with fewer than 6 inputs and a limited number of fuzzy rules can generate a very large number of rules, making their processing on conventional computers computationally expensive. Table 2 and 3 further demonstrate that medium and high-dimensional systems produce rule sets on the order of the millions. This exponential growth renders classical implementation inefficient. However, the same tables reveals that quantum computing offers a promising alternative high-dimensional fuzzy system can be encoded using quantum a moderate number of quantum circuits. The article also presents a quantum circuit implementation of a fuzzy inference system for a specific case involving 2 inputs and 4 fuzzy set values per variable. This serves as a foundational prototype for extending the approach to high-dimensional systems. For future works, we focus on a comparative analysis of output generated by quantum versus classical fuzzy inference systems. And we explore the relevance of type 2 fuzzy systems, which are designed to handle uncertainty, particularly to handle the noise sensitivity inherent in the current quantum hardware. Another direction is the development of or implemented reversible fuzzy norms and S-norm operators, with the goal to advance toward fully quantum fuzzy inference capable of capable of executing the entity inference process. These are the reference, and thank you for your attention.